digging now deeper and getting closer to more practical encryption ciphers that are used in practice. One of them happens to be data encryption standard, which belong to the family of block ciphers. So we are done with stream ciphers. We discussed them last 2 weeks. Now we will move into block ciphers that are more used in internet applications and mobile applications and so on, much widely used than the stream ciphers. There are many ciphers in this family. Among them is this data encryption standard. Now, what we will do, this is the outline, this is the goal of this session. We will try to introduce what DAS, and some people call it DES, others they pronounce it DAS. So I'll maybe use DAS. Introduction to DAS, then an overview of the algorithm, high-level overview, then going deeper as much as we can handle. And then we discuss how secure is DAS, and we will conclude that although it has dominated the cryptography field for 20 years, from I think late 70s to late 90s, now it's no longer the best algorithm out there. There are much better ones. Particularly, it was replaced by the advanced encryption algorithm, which is AES. AES is the most widely used right now, and for many years to come. But it is important to, it is still there, so it is not a waste of time learning about it. Not only this, some of the innovations introduced by this algorithm is adopted by the next algorithm. So it's not like starting from scratch. Some of the ideas are shared. Yep. So before I just want to motivate this much further, the importance of understanding these algorithms. We will open the box a little bit. We will see them from the abstracts from outside, and we have to open the box. So no longer it becomes like magic for us. We see the inner working of it. So to motivate this further, I decided to first start with some examples of using such ciphers. So what I'm doing here, I'll be using this PowerShell, and I'll be running some of the commands from OpenSSL. Your homework one of the tasks of homework one, you will be playing with these commands in certain scenarios. This is very important to get some hands-on with the practical cryptography. We will see some useful scenarios. So first of all, just to show you, if I go and use this OpenSSL and just ask it, what algorithms do you know? What algorithms have you implemented? I am asking this tool. Okay, hopefully it will be responding. Okay, so this OpenSSL minus dash ciphers, it will give me all the ciphers or algorithms that are implemented by this tool. It's a scary list of algorithms. One of them, you see the bottom half, one of them happens to be DES, DAS. And that DES is not just secure, so people try to fix it by doing the encryption 3 times, using 3 keys. It's much more secure, and they call it triple DAS. And there is the most famous one is, which one? EES. This is the most widely used. Now, EES has many modes of operation. So even as an end user, I mean, when I say end user, as developers, you still need to know some level of details of the algorithm, its mode of operation, what these, for example, what this 128 means, what this ECB means. This is what we will see in the lecture. And of course, we will also see how the inner working of it. So this is just to show you that what we're covering, it's not only conceptually getting the understanding of modern cryptography, but also you need it even when you are doing some developments, either using programmatic API or using some tool like OpenSSL. You still need to know some level of details of the algorithms and be familiar with the most famous and most important among them. And you can see we have even the one that we discussed last session, remember? RC4. It is still there also. It is implemented. This is, what type of cipher is this? It's a stream cipher. What type of cipher is this? DES and AES? These are block ciphers. Okay, very good. So you can see it's so many algorithms out there. So let's now start with, if I want to use this tool, I have a file and I want to encrypt it, let's say, and I want to send the encrypted file. Or it could be a string, I want to encrypt it and then send it over through the network. But here we just want to keep it simple. We will be playing with files just to demonstrate what we mean by modern cryptography tools. So the command to use to encrypt is OpenSSL encrypt. And you can ask it for help. You can say, what are the parameters expected? So you can see here is a bunch of parameters. Among them is which cipher you want to use. One of the algorithms is the cipher type that you want to use for the encryption. And others, it could be an input file and an output file. So you give it an input file and output file, and it goes ahead and encrypt it. So let's now take a look at some examples. Starting, and by the way, whenever you want to do encryption, you will need some kind of key. Some key. Usually, you can also use this tool to generate the key. I demonstrated this before. Like for example, if I want to generate a 64-bit key, for example, DAS that we will be discussing today, it needs a 64-bit key. To generate a 64-bit key, 64-bit is how many bytes? 8 bytes. 8 times 8, 64. So in here, I'm asking it, please go ahead and generate for me a random number of 8 bytes and give it to me in which format? Hexadecimal format. So I can copy this, come here and, okay, good, it's going well. All right, so this is the key. I can use this key as an input to my encryption and decryption. Yeah? Or I can, if I wish, I could store it to a file, and then whenever I encrypt and decrypt, I'll ask the encryption algorithm to pick up the key from this particular file. Okay, so this is what I want to say to do, like here it is. So I can, I generate a key, a random number of 8 bytes, and I output it to this symmetric key text txt. And this key, I could share it with the other recipient to be able to decrypt it. Of course, later on, we will see a secure way to exchange the key. If we exchange the key in a non-secure way, we are always wasting our time. If somebody intercepts the key, they can decrypt all our communication. So that's another story for next time, is how do you exchange the key in a secure way. And this is where, if you recall, there are, in the cryptography, we have symmetric, asymmetric, and we have protocols. One of the protocols is protocols for secure exchange of the key. We agree on a key without exchanging it. You will see, it's full of magic. It's thanks to a protocol that we will see later on. All right, so let's move on. So if I do this, it's created a file, and I can say here cat system.txt, and this is the file and the content of the file. It just has the key. Now let us start playing with some of the encryption algorithms. Let's start with a simple one that we already covered last time. Remember RC4? So in here, remember it uses very simple lookup table, 256 elements. It permutes those numbers, and it picks up one of the keys for every cipher text. Okay, so for every cipher, it's a pick up like a random number for every plain text letter. We've seen this yesterday. So let us now use this. So first, this is the file I want to encrypt. Cat, I think it's called plain text file. This is the file I want to encrypt. This is a famous sentence in English. Why it is famous? Because it covers all the letters of English. All the letters are in this sentence. So it's a very popular sentence. So we will use it as our plain text, and we want to encrypt it. All right, so here it is. So we copy this guy and then go here. And then, so let me explain what's going on here. This is the OpenSSL. OpenSSL has so many features. What feature I want to use here is encryption. What algorithm I want to use for encryption? RC4. So now this is not some scary cryptic input. You know what RC4 is. This is the reason why we are covering this in some level of detail. Now here, -k secret. This we will also see later on. There are two ways you can generate a key. One way is to do random number generation. You generate a random number and this is your key. This is one way of doing it. Another way of doing it is you use what is known as passphrase, some kind of password, and based on the password, the system will generate a key. This is what I'm using. Otherwise, I can pass a parameter, and the parameter will be the key directly. So you can either pass the parameter. By the way, if you pass the parameter, the key will be the capital K in this particular tool. If you do capital K followed by the key, that key will be used. Otherwise, you can do small lower k and give it a passphrase, and the algorithm will generate a key based on this passphrase. Of course, this password needs to be passed when you decrypt as well. So it will generate the same key. So key generation could be purely random, or it could be based on some password, let's say, some text. Here, this is the password I'm using, secret. This is not my key. You need to be careful. It's not the key. Here, this is the in. The input is plain text, and the output is ciphertext. -a, let me not use -a now. -a is just to do the decryption. Sorry, when it encrypts, it will encode the output in hexadecimal format rather than ASCII format. Okay, so I'll show you the difference. Now, if I do one more parameter here, -p, one more parameter -p, it will show me the key, the actual key that will be used for encryption. So let us run this. Here is the actual key that is being used. Based on this password, this is the key. Now the file has been encrypted, and this is the encrypted version, ciphertext file. Is the encrypted version. Yeah. Now, if you don't like this scary characters, ASCII characters, because once you go beyond 127, they become in ASCII code. They become like extended ASCII code. Some of them are very scary. Some of them are not even displayable. That's why it is recommended when you encrypt, you pass this -a. What this -a will do, instead of giving you this ASCII encoding, it will give you hexadecimal encoding. So if I do this, here is my key, and I'll do again, display the cipher. It's a bit more, especially if you are sending it through the network, or you are sending it by email or something, it's better to encode it in hexadecimal or base 64. So in hexadecimal encoding, what are the possible characters we can use to encode some particular message? 0 to 9, and then? Sorry? A to F, yes. So we have, and how many bits does it encode? One hexadecimal number. How many bits? 4, yes. So 1 byte, how many hexadecimal numbers you will have? 2. So each two hexadecimal numbers represent 1 byte. Yes. For example, if you see FF as an hexadecimal number, what does it mean in decimal? 255. Okay, which is basically 1 byte. Another encoding, which is base 64. Now, in hexadecimal, what is the base? How many characters we have in this encoding? 16. So it is base 16. Like, for example, the decimal numbers we are familiar with, it is base 10 because it goes from 0 to 9. Now, base 64, it is base 64. So how many characters we have? 64 characters. And definitely we have 0 to 9. Then we have A uppercase to Z uppercase. Then A lowercase to Z lowercase, and then some extra characters to make up the 64. And how many bits does it encode? So hexadecimal encodes 4 bits. Yes? Now 64 will encode how many bits?
6.
Sorry?
6.
6. Why 6?
2
to the power of 6. Okay? So that's basically the idea. It's similar to hexadecimal, let's say. But instead of using 16 characters, it uses 64 characters. And instead of encoding 4 bits at a time, it encodes 6 bits at a time. That's what base 64. This is very famous, very widely used encoding. We can read a little bit of it more. Just maybe, hopefully, I can show you. Okay, this is the index table. These are all the the characters you can use in base 64. So as I mentioned, we have 0 to 0. Oh, 0 to. No, we have A to Z, then small a to small z. Yes. So these are the index of each of these characters. So it doesn't not like the hexadecimal. It starts with digits first, 0 to 9, then A to F. It starts with A's, the uppercase letters, then the lowercase letters, then the numbers, then it's fill up the last two, because it's 64 characters, plus and the slash. It's kind of clear? So that's what this is doing when I say here dash A, it encodes the output using base 64, which means what you will see here, what are the characters you will see here? One of the 64 allowed characters, which is the A, from A to Z and uppercase, A to Z lowercase, 0 to 9, and then plus and slash. That's all you see here. You don't see this scary text. Is clear so far? Okay, so this is the magic. This is the magic of the encryption. We took a plain text file, we put it through an algorithm, we fed it to an algorithm, to a cipher. We fed the plain text. What else we fed to the algorithm? The key. Thank you. The key. Then what it gets produced? Ciphertext. If you want to scale everybody, you can keep it as it is. But when you transmit it, you might have a bit of issue, especially if you have some legacy applications that cannot handle some of these characters. Especially, and some of them might be non-displayable. You cannot even see them. Now it's better because in ASCII, even the tab and the delete and those buttons that you don't see them in the screen, they also encoded. They also have numbers in ASCII table. Yeah. By the way, I think yesterday I found one very nice ASCII table. I'll add this to my. Okay, let me see it. RC4, yes. I will add it to the resources. I think this is very nice. Best ASCII table I ever seen on the web. Last time we tried to look up some ASCII table, it was very fiddly. Here is a nice one. Here are all the characters. You see here, if you happen to see 07 or 7, it is a bell. It's kind of some kind of sound, backspace. These are not displayable. If your encoding happens to fall on those, then it's a problematic for transmission. There is even carriage return. It starts getting this. These are all what they call themselves control characters. These are not displayable characters. And then we have the ones that we are familiar with. These are printable characters. That's why we see this these characters that don't make too much sense because of this encoding. These are all the ASCII encoding. This is the number, and this is the corresponding letter. It's okay, thank you. It's telling us all the details. This is the decimal value, the hexadecimal, the binary value. It's very nice if you need to somehow use it. Okay, and then we have the special characters, extended. Before it was up to 127 mappings. Now it was extended to, I think, 255. And you get all these funny characters here, up to 255. Yes? And if you want to look up something, like for example here, A, it gives you exactly what is the decimal value corresponding to it, what is the hexadecimal, what is the binary. Okay, so here is we use a cipher, we use a stream cipher to do encryption, which is RC4, but we know this is not safe. This can be broken. This can be attacked easily. So now we go for more advanced encryption algorithm. It will do the same. The same goal is to scramble our text in a way that nobody can make sense of it except if they have the key. So let's do DAS. Again, the same thing. The only thing I'm changing here is the algorithm. Instead of using RC4, I'm using DAS. And all other parameters are the same. So it went ahead and encrypt. If I do here cat cipher text, this is my cipher text. If I don't like this representation, I can do encryption with -A to make it base 64. If I do encryption here, and then I do the same thing, it's now base 64. Now, if I want to decrypt, I use exactly the same thing. Of course, I have to do -A here to tell it that the cipher text is in base 64. So the only thing here, I am passing one more parameter, which is -D for encoding. And what I am giving as an input, cipher text, what I am producing is decrypt output. Let me redo it. I do -P just to see the key that was used. This is the most important. This is the key. This is used. Now this DAS requires a key of 64 bits. DAS requires a key of 64 bits. This key, what is the encoding of this key? It's hexadecimal. So 64, how many hexadecimal will be? How many hexadecimal characters? 64 divided by 4. So that's 16, yes? Yes, 16. I just want to see the length of this key. Yeah, the length is 16. Yeah, so 16, which means every character, as we said, every character in the hexadecimal represents how many bits? 4. So 16 times 4, 64. So DAS requires a 64-bit key. But when we produce these keys or use these keys, we don't put the binary format. We use the hexadecimal format. Okay, so you might be confused. Oh, this algorithm needs 64-bit key. I'm giving it 16 characters. What's going on? No, these 16 characters are hexadecimal. When you convert them to bit, they will become 64 bits. Okay, now just to see that the ciphertext was created, so I do here cat cipher. Here's my ciphertext, and now I want to decrypt. I want to decrypt. Here is the decryption. Okay. So the only difference compared to encryption is this flag here, -D. Go ahead. You can see here the exact same key was generated. Yes. This is the key that was used for encryption, and this is the key that was used for decryption. So what's going on here? You could generate your own key and use it as an input to encrypt or decrypt. That's one way of doing it. Another way of doing it is you give it a passphrase and you let the, in this case, OpenSSL, to generate a key for you based on the passphrase. As long as you are using the same passphrase in both, then you should be fine. It will create for you the key. Now, the key generation is itself is a story that we will cover later on. Here, our focus here is just to give you a taste of modern cryptography and give you the taste of how it is used in practice and how you need to get some understanding of the inner working of the box to be able to at least use these tools comfortably and do the right choice. Because you have so many ciphers, so many parameters, and you need to do an informed choice. Not using your flowers, say I use DAS or ES, and which parameter I use 128 or 256, which mode of operation. You really need to have good understanding of these algorithms to be able to effectively use them and effectively explain your choice. Cat decrypt output. I'll get back my original text. Yeah. All right. So this is still not too scary. This technology, this cipher DES was invented in the mid 70s. Okay, by IBM and NSA. This is National Security Agency. Okay. These are the people behind this DES. So it's not something simple. It took a lot of investment, a lot of innovation. When I say NSAs, this is the headquarters. It just gives you an idea what they are. And their budget, this is a leaked budget, $10 billion budget. So this is not something light. This is very serious matter. Encryption and decryption is something very, very important. It's a national security concern. Yeah, and we will see the story behind this and how this evolved. And AS, like the advanced encryption standard, it took maybe 4 or 5 years to develop. But this one was like DAS was developed behind the scenes. Okay, like in closed doors. Advanced encryption algorithm was open. They made an open call for proposals. And all the cryptographers of the world, all the smart mathematicians, they made the proposals. There were 15 proposals, and then they took 1 year to study them, and then they shortcut them, the shortlist 5, and then among those 5, they zoomed in, they selected one, and that became the standard. And during all these 4 or 5 years, all the smart crypto analysts, you see here, cryptographers, they come up with these ciphers. The crypto analysts try to break them. And the ones that is very hard to break is the winner, basically. That's how it works. So this is these little, you might see these little tools, we just passing a flag. It took a lot of investment to do so. Yeah. And initially it was all this top secret, initially, especially DAS. Then it became like public. So they made it mandatory if you want to, between the mid-70s up to 2000, if you want to talk to US government, send a document or receive document, let's say the president wants to send some letter to Doha embassy, US embassy, they will have to encrypt the message using DAS at that time. Now the new encryption algorithm mandated by US government is Advanced Encryption Algorithm, AES. So any classified communication must be encrypted using that algorithm. Yeah? And if something like, or some organization like NSA chooses that algorithm to encrypt their top secret classified document, then you just close your eyes and use it, because they really know what they are doing. They have the manpower, they have all the manpower, the $10 billion to invest in this. So this is not something light. There's a lot of innovation there. It's almost magic, as we will see. It's very exciting to see how these things work, because it's really magical, to be honest. It's mind-blowing, And when you start looking into the inner working, you will see how this is done. Yeah. Okay, so let me do one more example. Here it is. This time I'll be using triple DAS. DAS, although we will see it and you will see how amazing it is inside how it works, it's still, people manage to break it, but not mathematically, not using some mathematical kind of technique, but they manage to break it using brute force. And we have to wait until 2020 years for somebody to be able to break the key. Using what? Brute force. That's the only way. Because of the improved computation power, people manage to break it. And then once they break it, khalas, you have to move to some other system. That's what happened with DAS. But it's still there. It's still very secure, but breakable. Now, the next version, or while they are working on the next version, because it took like a couple of years to come up with the next version, they just quick fix, which is the triple DAS, which basically it does encryption, as I said, DAS 3 times with 3 keys. The problem with DAS, why do you think DAS was, people were able to break the key using brute force? Why do you think so? Sorry? Sorry, I didn't hear. They didn't? Close, a little bit more. Why it is breakable? Thank you very much. The length of the key is with the current computing power is 2 to the power of, what is the length of DAS? The key, the 64 bits. So what is 2 to the power 64? You are not awake today. Okay, no problem. I can understand. And by the way, 64, this is effectively, it doesn't use 64. Although you feed it 64, effectively it uses 56. So I know I don't burden you with doing this. So let me ask our friend to do it. Okay, this number of times. So if you look if you have some ciphertext and some plain text and you don't know the key, you can do a loop from 1 to this number and you can break the key. These days, with some powerful computers, you can do it. Yeah, that's why it's breakable. Now, triple DAS, it uses 3 keys and 3 encryptions. Encrypts with 1 key, then encrypts with the second key, then encrypts with the third key. What will be the length of the key? Okay, so let's just consider it 50, although because we will see later on, it doesn't use the whole 64, it uses 56. So this is times 3. If I run this guy, you have this much number of iterations. This is not breakable with today's technology.